Thank you. And that was a great talk, Haley and Zach. That was a really good overview of both techniques. So we're going to change gears here a little bit, and we're going to talk about math and its application to chromatography. So two high points that both Haley and Zach kind of mentioned is multidimensional chromatography yields complex data. And for some simple analysis, yeah, maybe we can look at the chromatogram visually and say, hey, there's an obvious change there. But when we get to really complex samples like petroleum, metabolomics, high explosives for my work, things get really complicated. And we add in mass spectrometry, especially high resolution mass spectrometry. When we're working with the raw data, we can be talking about 4 billion data points, which is just kind of mind-blowing to say that we can do that with computers now. But as humans, we cannot look at 4 billion data points and get any useful information out of it. So we obviously don't want to visually compare complex samples. We definitely don't want to make peak tables, and especially in my case, everything is an unknown unknown. It is never in the NIST library, so trying to identify it doesn't really help us. And most of the time when I talk to our program managers, they don't care what the identity is. So they want to know, are things different? And if the answer is yes, they want to know how different. If they're not different, they don't care, and we move on. So we really want to spend time, if we do need to identify stuff because something changed and we really need to know that answer, we only want to work up what we have to, because figuring out those unknown unknowns is kind of a pain. So there's a lot of different chemometric techniques out there, and I'm only going to hit some of the high points here. There are thousands of paper for chromatography and chemometrics, but we can kind of break them down maybe into like 3 classes where we have classification. So we want to know, how is this one sample different from this other sample? We can do feature selection, where we can kind of hone in and look at the chromatograms and say, hey, this compound is changing across, or hey, I ran this experiment where I changed something biologically, how do the metabolites change? Or we can do property prediction, right, where we can say, hey, I have this chemical information that I obtained from GCxGC in this case, and I want to predict the properties of rocket fuel. So all these techniques are really great, except for when you try to look for trends. So if you have a compound that's changing across a series of chromatograms, and it's very subtle, none of these techniques are really the right way. And that's very common for us, where we have explosives that age, and we need to know what compounds are changing as a function of this aging. So we recently kind of adopted these techniques from the spectroscopy world and applied them to GCMS, LCMS. So the first one, alteration analysis, that's a quantitative understanding of how individual data points vary across samples. And I'm going to give some examples here. And then we have our 2D correlation. So once we've quantitatively identified what's changing in our chromatogram, we can then understand the relationship between those changes. So if we have compound A turns into compound B splits and turns into compounds C and D, we can say, hey, all 4 of those are related, and we can explore that relationship. So time for math. So ALA, right, we have a series of chromatograms in here. This is just 1D, and I've generated this data. So we have a peak on the left there. It's just linearly increasing, and then the peak on the right, it's exponentially decreasing. So for ALA, we can generate these 3 maps. The first one is called the BAM, the basic alteration map, and we just take the maximum and we subtract off the minimum. Pretty simple math there. And so we can see the peak on the left change the most, therefore the BAM is going to be the highest. Now the math gets a little more complicated. So next, we can calculate our difference matrix, that's just the differential, and then we can take that information and apply it and generate a SAM and an AM. What that describes is how linear and nonlinear our changes are. So math looks really complicated. It's actually really just like 2 lines of code in MATLAB. But we can use that information to understand how linear a change is and how, I guess you could say, nonlinear changes. So we have our amplitude of the change and the type of change that's happening. So if we think about those other chemometric techniques I just mentioned, Fisher ratio might say, hey, there's something happening here in the chromatogram, but it doesn't tell you over a series. Or PCA, great technique, but it doesn't really work on really subtle changes. So we explored how does ALA work for GCMS, LCMS. So we generated some fake data, and so on the top there you can see I generated a bunch of noise, I calculate the BAM, SAM, and AM, you get back noise, yay, our technique kind of works, we don't find anything, which is the correct answer. And then we can do a linear increase where we take our samples and we increase our peak area only 1% every single time. And this is at initial signal noise of 75. We can calculate our BAM, SAM, and AM, and you can see a peak appears. We found something. And we even explored this and showed that ALA works for peaks that are severely overlapped. And they can be even extremely traced, so very, very subtle. So you can see I've zoomed in way into the baseline there to see that very subtle change that was overlapped by that massive interference. And yet, we can still find that with ALA. So now that we've discovered our statistically important chemical compounds that are changing, we want to understand the relationship. So again, going back to my degradation sample, we have A becomes B, becomes C, becomes D. We find all of those with ALA. Now we need to know how are they related. So we can take our 2D core here. So we can generate our synchronous and our asynchronous maps. Again, more math. I'm just going to refer you to go read our publication. But let's apply it now. So, hey, I have 6 peaks here, and they got all kinds of different changes. I can generate my synchronous and my asynchronous maps. And explaining 2D core, this is coming from the spectroscopy field. This is my collaborator, Matt Herman, had to explain this to me multiple times on how to read this, because I look at it and I see a GCxGC chromatogram, and it's not. It's more analogous to more like 2D NMR. This is kind of how it is. But the information that we can get from 2D core is we can see our peaks changing in relationship to each other. So that first peak, the way to read it is we have our first, second, third, fourth, fifth, and sixth peak that are highly overlapped. So here we have a negative value. So we know our first peak and our second peak are anti-correlated because the value is negative. So that means either peak 1 is going up and peak 2 is going down, or vice versa. We don't know which direction, we just know it's opposite, and we can go through and interpret the entire map. The asynchronous tells us the rate at when things are happening in time. So this change happened first, and this change. So using Noda's rules, what can we get from 2D core? We can figure out the order of which things happen. And that's important for us in degradation, because we want to know, hey, we have this explosive, and it's going to decompose. What is the first step that's going to happen? So we wrote a nice publication on this and then got, okay, well, this works really well for 1D chromatography. We do 2D chromatography. We need to make it work for that too. So we all know whenever we collect a GCxGC chromatogram, right, the peaks are never exactly in the exact same spot down to the exact data point. So thankfully, there's been some excellent work by Rob Sinovic and a lot of his grad students who developed this tiling and applies Fisher ratio for that. So if we tile our data, we can overcome this misalignment. And this is really important actually for 2D core, because when you do 2D core calculations, your original data set becomes squared. So you take your 4 billion data points, and now all of a sudden, it gets really big, and your computer crashes. So the tiling really solves our 2D core number problem here. So we apply this to some explosives I'll talk about on the next slide here, and we have this procedure, very similar to those of you who have ever used the tile-based Fisher ratio or Chromatograph tile. This is kind of like the same parameters, except instead of doing Fisher ratio, we're going to do ALA now. The important step is number 4, 5, and 6. So we calculate our ALA parameters, and then we can calculate a signal to noise, just like you would for chromatograms, except it's now in ALA space. And we recognize that like a signal noise of 10, everything below that, it's like a 10 to the minus 23rd chance that it's going to be, not going to be real. So we pick that. We scale our BAM, SAM, and AM to 1. And then we enforce this requirement that you have to have a BAM with a signal release greater than 10, and then a SAM and an AM. So what that does is you have 10 to the 23rd. We didn't take the math any further, but pretty much if you detect it with a BAM and then a SAM or an AM, it's a guaranteed statistical change. We can go through, remove our redundant hits, and then we get this nice output. And we applied it to high explosives. So for those of you who are not familiar with this, I talked about this at the last MDCW. So we took high explosives and we put them in our GC and we cooked them until they decomposed. And then we did a 2D separation on all the different decomposition products. And when we did this, we're like, okay, we're going to get like 5 or 6 things. So we were actually doing it in 1D. And Colleen, who made this technique work, was like, wow, there's a lot more than 2 things there. There's like hundreds and hundreds of things that we're identifying. And in the past, we had used Fisher ratio for this and even aging experiments before. But the problem is we always would compare our beginning state to our end state. And so if we had any intermediates, Fisher ratio would not identify them. And so we would go on the assumption that if we saw something in the end, it would be progressed through those middle chromatograms. That's not always the case because we would have compounds that would form as intermediates, and by the time we would get to the end chromatogram, they'd be gone and we would never discover them. So in this case, Colleen discovered 250 plus chemical changes. We kind of like went down the list, and eventually they get not as significant, and it takes a lot of time to identify unknown unknowns, even with high-res mass spec. So we found all these chemical changes, but we didn't have the 2D core. So Colleen and the organic chemists had to get together and start drawing pathways for this explosive and then the decomposition of that explosive. So it got really complicated, and I'm a terrible organic chemist. So I want to have the math tell me. So for 1D GC, for 1D GC, what we did is we'd take our ALA, we would essentially sum away our mass spectral dimensions, so now we essentially have a 1D data set. We can calculate our 2D, it squares it, so now we have 2 dimensions. So while we remove the mass spectral information for our 1D separations, we can see the relationships, and visually we can look at the synchronous and asynchronous maps. Everyone's happy. The problem is when we take our GCxGC data sets and we square them, we now have 4D data, and it forms a tesseract, and it's impossible for humans to interpret that. So we could just let the software do it, but then we have to push the I believe button every single time. And the program managers, they don't understand. So we need to figure out, how do we make our GCxGC data 1D? So we take our ALA and we refine it a little bit. So we have our initial output where we have essentially our hit table, and it's ranked by our BAM values, we have our mass channels, we have our retention times. And what we do is we know the retention time, and we can recenter our tile on that retention time, and then we're going to recalculate our ALA parameters. So those for you who are unfamiliar, right, the tile is kind of, it's not random, but it's very rigorous, where it's just essentially one tile and another tile, and it's stacked up right next to each other. So whenever you tile your data, you don't perfectly capture that peak. And so we were thinking for our 2D core, we need to perfectly capture our peaks. And we also want to understand the relationship between ALA and 2D core, because we have our quantitative and our qualitative. So we're going to recenter our tile, recalculate all our ALA values, and now we have tiled data. That's essentially a single data point. That's kind of 1D GC-esque. So we can take our data, we know what mass channels are statistically significant within that tile, we can sum all that away, and we can then generate our synchronous and asynchronous maps, and most importantly, we can determine our order of change. So let's see it in action. Now I've been talking about math, let's see it in reality. I thought, hey, we had this previous explosive data set, I'd like to show you how 2D core works on that. And when you try to interpret it visually for 250 compounds, it's really interesting, but not really good for giving a talk on. So I made some fake data here where I can control it and make things a little bit easier. So we have our GCxGC chromatogram in the top right there. So there's 50 peaks there, and I made 8 of them change, and you can kind of see the change down below. So some of it's linear, some of it's quadratic, some of it's exponential, and for a little bit I was even playing with some sine waves where our peaks would wobble like this. It makes the interpretation really weird because it's neither the first thing that changes nor the last thing that changes. So, for our real-world example, talking about that aging of the high explosives, we have 10 chromatograms, and we took our explosives and we cooked it at different temperatures. So that's our 10 chromatograms. So you can imagine our explosive X, which is going to decompose, but those decomposition pathways are maybe intertwined. One is probably more preferred than the other. We want to know all that information. So with ALA, we can easily identify, hey, there's our 8 peaks that are changing. We can then generate our synchronous map and asynchronous map, and we can get all this information very quickly. So the math on this is almost instantaneous. It's about 10 seconds on this data set, and we can now know our retention times, the magnitude of that change. Is it synchronous, asynchronous? Are mass channels that important? How interrelated everything is, and then the order of which things are changing. And so what's interesting here, even though I controlled this data set, it was a little bit of guess and check. You just put the numbers in and keep generating the data set until you get a nice pretty answer since it's all random. But the most important change is not the first one. And so whenever we think about like an explosive aging study or decomposition of pharmaceuticals, we might say, hey, that's a big change there. And statistically, that might be the most important one, but it's not necessarily the first thing that happens. And so if we're trying to draw these decomposition pathways with all this information here, now we know, hey, this is a key marker for us to pay attention to, but it's not the first thing that happens. So if we get all the way down to here, our explosives have aged pretty aggressively, and that's a problem. So with that, I have to acknowledge some people who helped pay for our instrumentation and time, and especially Colleen, who was essentially the beta tester for the ALA GCxGC code. She definitely was angry at me because I miscoded some stuff sometimes. And to Michelle, who is very pregnant right now, says hello to everyone, who is also the beta tester. And with that, I'll take some questions.